okay, we've talked about the derivative as a function. In math, we should always ask, does that thing exist? And so we have a word for this. Our definition, f is differentiable at a number a if f prime of a exists at a. So remember that the derivative is a limit, and limits don't always exist. So this is a really good question to ask. Underneath the hood, we're asking, does this limit converge? Now, in some cases, this is pretty nice and easy. Where are x squared and square root of x differentiable? Luckily for us, we've already done these. So for instance, if f of x is equal to x squared, we know what f prime of x is. It's 2x. And we can use that. So all this is asking is, what is the domain of 2x? And the domain of 2x, this is just all x. Or for all real numbers, or if you really like notation, which I do, all real numbers has a neat notation. It's like a capital R with an extra line in here. It's supposed to be a boldface R. So feel free to use that. But we can't hope that every function has a derivative everywhere. For instance, the square root of x isn't even defined for negative numbers. So let's throw in a little bit more notation here. If I took the derivative of the square root of x, we just found out that that derivative of square root of x is 1 over 2 root x. Okay, so this function, we know, needs x to be bigger or equal to 0 just to have a square root. But also we can't be 0 in that denominator, which means that that equals doesn't belong there. It's really just x bigger than 0. And this might be some comfort if you know how to graph the square root of x. It looks like this. And what we're saying is we're not going to include that endpoint there. Okay, so if we happen to know for sure the derivative as a function, then saying it's differentiable just means we're in the domain of that derivative function. Now, there are three main ways that we could not be differentiable. In fact, maybe I'll hide this from you for a second. The first way we could not be differentiable is to not be continuous, to have some hole or jump. And you might ask yourself, how might I not have a derivative if I am continuous? And there's two ways we could do that. We could have a corner, right? Some kind of a sharp edge, or we could have a vertical tangent line. All right, let's think through these a little bit. This is definitely an easy kind of a quiz question for yourself in terms of, do you understand differentiability? So to be not continuous, there's lots of ways this could happen. You could just have some kind of a jump happening, or you could have just not being defined, or you could even have maybe like a hole with a point up here or an asymptote. In each one of these cases, that limit won't exist. The limit that defines a derivative. The limit from that limit is going to have some change in your y in it, and in this case, that change in your y doesn't go to 0 from the left and the right. Right? It kind of goes to different places, and so I encourage you to play around with that definition for a function that you know has one of these problems. I'll be more explicit with a corner. What do we mean by a corner? Well, here's a great example. Absolute value of x. Absolute value of x is continuous. There's no holes, breaks, or jumps. But if you graph it, it has this sharp corner right here. And so the limit on the left in that derivative is going to say, oh yeah, -1. And on the right, it's going to say +1. But because of that difference on the left and the right side, it won't have a derivative. And you could think of this too as trying to graph that tangent line. Which tangent line should you do? I don't know. There's like a lot of options there, and your limit also can't decide for you. If I was going to take the derivative of absolute value of x, you would get a piecewise function, and it's going to be -1 if x is less than 0. That's this whole area over here, or +1 if x is greater than 0. And that's this whole area here. Notice that 0 is not actually there, right? There, it's not part of that domain. So it's not differentiable at 0. Okay, and the last one might take a little bit of thinking. A vertical tangent line. So I've got a nice example of this. X to the 1/3. So I don't have an equation, or rather a vertical tangent line as a line. It's not a function, right? It doesn't have a slope. We don't have a slope of infinity for this. So if I was going to try to graph x to the 1/3, it is the inverse of x cubed. Okay, so it looks like x cubed, but reflected over the line y equals x, something like this. It's not a horizontal asymptote. It keeps going, something like this. And that tangent line right there is nice and vertical, so that is an infinite slope, and that the limit for the definition of a derivative is going to go off to infinity, and thus not exist. Just as a quick refresher on this, if I was going to try to graph y equals x cubed, y equals x cubed looks kind of like this. These two things are inverses, and so they should look like what happens if you switch the x's and the y values, or if you reflect over the line y equals x. Okay, so if I do this better, this should be horizontal right at 0. It should have a derivative of 0 at 0. And so when I flip that over, I get this infinite derivative, and we don't have infinite derivatives. That's just going to not be differentiable at 0. That's really it. Those are the 3 ways that you can be not differentiable. So let's go ahead and see if we can give that a try. See if you can figure out the places where this is or is not differentiable just by the graph. Now hopefully, if you're playing along, you realize, oh, actually it's easiest to look at where this thing is not differentiable. So which x values don't? Well, at 1, you've got a corner. Looks like at 2, you've got a discontinuity or a jump. And at 3, you've got another discontinuity. So it's everywhere except for those. So there's nothing wrong with this function, and this function is even continuous at 1. It just doesn't have a derivative. I also want to point out that a function has to be defined to have a derivative. If it's not defined, it's definitely not continuous, and thus doesn't have a derivative. If you have a derivative, you must be continuous, and so you must be defined. It's one of these logic games, right, where it goes one way but not the other. Okay, that is it for differentiability. Next up is going to be higher order derivatives.